All right, hello everyone. I am going to walk you through the next assignment you guys are going to do. I would like you guys to do a POGIL on torque using a FET. What in the world? So many letters. POGIL, if you guys aren't familiar with, is Process-Oriented Guided Inquiry Learning. So essentially this is going to walk you through the idea of torque. It's going to define some things, you're going to do some calculations, and you're going to learn what torque is going through this. FET, we've used these before, Physics Education Technology. That's going to be the simulation that you use to go through and learn about torque. So the purpose, we say this POGIL is designed to introduce students to the concept of rotation, specifically torque. So you're going to need a little bit of background information. You're going to need some basic terms defined. One of them is, well, what in the world is torque? Torque, we can say, is a force at a distance from an axis of rotation that causes rotations. So in the most basic level, torques cause rotations. So for your example, if you're ever, when you go to open a door or open a cabinet, you have to apply a force at some distance from the pivot point. So when you open the door, you use the handle, which is not right next to the hinge, and that causes the door to rotate. So if I draw a nice little top-down view of this door, here's the door hinge. You're going to come, here's your door handle. If you apply a force on the door handle, you are going to get this door to rotate. So that force causes that rotation, it causes a torque. Okay, so that's torque. Torque, we use this letter, it's a Greek letter, tau. The radius is the distance from the pivot point. So whatever pivot point you have, wherever it's going to rotate, how far is the force from that point? That's your radius. And then angle is the angle between the force vector and the radius vector. In this lab, it's always going to be just 90. So for example, if this is my radius, this is my force, the angle between those is 90 degrees. They are definitely not always 90, but it's easier when they're 90, so we're going to keep them 90 for now. Then we're going to talk about something called rotational equilibrium. That's when the net torque on the object is 0. I'll talk more about that later. And the units of torque, if we're multiplying forces times distances, we're going to deal with Newton meters. So our little formula for torque, we're going to say that torque is equal to RF sine theta. So how far away is your force times how big your force actually is times sine of the angle between them tells you the torque. So the further away your force is, the greater the torque, and the greater the force, the greater the torque. Both of those should hopefully make sense. That's why the door handle isn't at the hinge. If you ever tried to open a door by the hinge, if I, pulled really, really hard on the door right there, it's not going to rotate easily. We don't do that. That is a smaller torque. That's why we want the door handle all the way at the end. Increases the torque, makes it easier to open the door. All right, so what you're going to do in this lab to play around with some of this stuff to hopefully make this make more sense, you're going to go to this link in your browser. I have it open right here. You're going to click on the play button, and you're going to do the balance lab. So we're going to click on this play button. It's going to open. You're going to do the balance lab, and you're going to get this. First thing you want to do is remove those, I don't even know what to call them, supports. There you go. Remove the supports so that this thing will rotate, and you can see you have a little seesaw. What happens is, if you look over here, I can take a 5-pound brick, put it on, and it's going to rotate. That mass gave a force that caused this to rotate. I could put one on the other side and try and balance it. Hey, Now we're balanced. There's a whole bunch of masses over here. There's people and there's mystery objects. You're going to use those mystery objects, but we don't have to worry about it yet. You can put a ruler on. I would suggest you do that. Marks, nah, go with rulers. If you want to show the forces, you could do that too. You can see the 10 kilogram has a greater white arrow down than the 5 kilogram. And level if you want, but you don't have to do that. All right, so that's what your simulation looks like. You're going to go through and do a couple things with it. You're going to first just play around. It says play around with various masses and radii on one side of the balance beam and remove the supports. Notice the difference in how quickly the balance beam rotates when masses are placed at different radii. Does it rotate faster when it's closer or further? So just play around a little bit. Place bricks at different locations along the right side of the balance beam and calculate the torque. Use the ruler provided for your radius values. So stay on the right side, put a mass, calculate the force of gravity, give me the radius. Remember, radius is measured from your point of rotation. So if we have this 10 kilogram object, it is 0.75 away from the rotation point. So you could figure out the torque saying RF sine theta, but remember theta is always 90 and sine of 90 is 1. So it's just your force times your radius. So just play around, do a whole bunch of different ones, whatever you want, make up those values. Then what you're going to do is now we're going to start talking about multiple masses. The way we can define multiple masses, if the rotation is counterclockwise, we say that it's a positive torque. If it is clockwise, we say it is a negative torque. So if you have one on the left, one on the right, you can figure out which one is bigger. If it's negative versus positive, you can tell if it's clockwise or counterclockwise. So mix them up there, do multiple mass 1, radius 1, torque 1, mass 2, radius 2, torque 2. Keep in mind the direction, and then figure out the net torque. All right. Then you come up to this guy. It tells you where to put some masses, and you want to figure out where to put the other masses. So you want to balance the balance beam and fill in this chart so that the balance beam is balanced. I mentioned rotational equilibrium earlier. Rotational equilibrium is when we are balanced. My net torque is 0. So if I have a 5 kilogram mass at 1 meter, where does a 10 kilogram mass have to go so that it's balanced? Fill that in. Go through, do all of these. The last one right there, well actually the last two, has 2 masses to add, so 3 masses total. The first guys only have 2 masses, the last 2 have 3 masses. Then what you want to do is you want to figure out the mass of the mystery boxes. So essentially put your mystery box on one side, figure out where you want to put it, put other masses on the other side, then use the math to figure out what the mass has to be based on what masses you use to balance. Some of these masses will need multiple masses to balance, so if you need to use multiple objects, that's fine. Sometimes you'll need to use the people, so you have like 5, 10, 15, 20. Well, the people are, 20 and 80, 30 and 60, so you might need to use them. So if you put the object A over here, it's going to rotate. You have to figure out where to put a mass so that it's balanced. Too much. Play around. All right, so now it's balanced. Maybe not. So you get the point though. You got to figure out how to balance it. And then once you know the balance, you can do your math to figure out, if you know the torque on the left side, what's the torque on the right side. So you can figure out the mass of the box. And I'm struggling to get this to balance. Let's try the 20. Ah, I did it. So essentially, if I know the, wow, so this math on this one's really easy because I put them both at 1. So there you go. I just did A for you. The block of A has to also be 20 grams since they're both balanced, kilograms since they're both balanced at the same location, away from the pivot point. Does that make sense? Hopefully that makes sense. Go through, do all the different boxes, and then you're done. Yay! If you have any questions, let me know. Torque is fun. I think it's cool trying to balance it. Hopefully you guys can figure it out. All right, awesome. Have a great day.